Yeah. Next topic is Cauchy's theorem. Cauchy's theorem, or before going to Cauchy's theorem, we need some basic concepts to define Cauchy's integral theorem. The first one is simply connected domain. Simply connected domain or region. Simply connected domain or region. What is the definition of this simply connected? Simply connected means not simple. Okay. See, a connected domain. A connected domain. Connected domain means there is no discontinuity in that domain. Okay. A connected domain is simply connected. A connected domain is simply connected. Is simply connected. Simply connected if every simple closed curve, every simple closed curve, every simple closed curve inside D, inside domain D, inside domain D encloses only the points, only points of D, only the points of D, only points of the domain D, only the points of the domain D. So now here there is one word, simple closed curve is there. Let me define that one also. Simple closed curve. Simple closed curve. What is the definition of this simple closed curve? A curve which does not intersect itself, which does not intersect itself, is called simple closed curve. Is called simple closed curve. This is the definition of simple closed curve. What is the meaning of this? For example, if I take one curve like this, this is the curve C. Is this curve anywhere intersect itself? Simple closed curve, and it must be closed. Remember, it must be closed. A simple closed curve. For example, if I consider a curve like this, this is curve C. It intersects itself. Not a simple closed curve. Not a simple closed curve. Not a simple closed curve. Okay. Now, I think this is simple definition. Simple closed curve means a curve which does not intersect itself is called simple closed curve. If it intersects itself, it is not a simple closed curve. And based on the simple closed curve, the first definition is simply connected domain or region. What is the meaning of this? A connected domain. Connected domain means, see, this is the domain D. Okay, this is the domain D. Yeah, this is everywhere connected. Connected means if I consider any 2 points in the region, okay, and if I join those 2 points, whatever the line or the curve must be belongs to within D. Must be belongs to within D. Okay, that is called connected domain. Now, what is a connected domain is called simply connected. Simply connected if every simple closed curve inside D encloses only the points of the domain D. For example, see, if I consider this one, simply connected, I have to consider only simply connected. See, let me take, for example, to get the idea, okay, this is one curve C, simply connected, and this is the domain D. If I consider any simple closed curve inside D, any simple closed curve, choice is yours. Simple, I have to consider what? This one, simple closed curve C. Okay, not this is, I'm taking this as curve C1 and I'm taking this as C. See, the simple closed curve having so many points which are belongs to what? Domain D. every point inside the simple closed curve belongs to D. Belongs to D. This is called simply connected domain. Simply connected domain. Okay, that means let me write a simple definition of simply connected region. A domain is said to be otherwise. Simple logic. Otherwise, see, this is all points are here. These are the points of the domain. And what are these black color points? These are the points inside the simple closed curve C, which are also belongs to what? Which are also belongs to what? Curve domain D. A domain is said to be simply connected. A domain is said to be simply connected. See, I'm giving one simple definition. A domain is said to be simply connected if it does not contain holes. If it does not contain holes, right? If it does not contain holes, that means what? Exactly. This is one curve C. This does not contain any hole. So this is simply connected. This is simply connected domain. Simply connected domain. If I consider, for example, circle, this is curve C. This is also simply connected, right? This is also simply connected. But if I consider concentric circle, what is meant by concentric circle? Concentric circle means, yes, this is domain D, which is bounded by two rings, which is bounded by two curves. This is concentric circle. Now that means what? Your ring, for example, your ring. This is concentric circle or annulus. One can say this is annulus. This is the domain D. It contains holes. This is not a simply connected domain. Not a simply connected domain. Because it contains holes. Because it contains a hole. How many holes are here? Only one hole is here. Okay. And for example, this is one region. This is curve. See. And this is one hole. This is another hole. This is another hole, like that. This is, where is the region? Domain D is only these parts. Only these are the points on the domain. Not inside these holes. Holes having empty. Okay. Those are empties. This is not a simply connected. Not a simply connected domain. Contains how many holes? 3 holes. Not a simply connected domain. I think this is clear. Simply connected region and which is not a multiply. Now another definition. What is that? Multiply connected region. Multiply connected region or domain. What is this definition exactly? All these which are not simply connected. A domain which is not simply connected. A domain which is not simply connected. Which is not simply connected is called a multiply connected region. Is called a multiply connected domain or region. That is a domain having holes or containing holes. A domain containing holes is called multiply connected region. Is called multiply connected region. Multiply connected region. Any doubts in this topic? Simply connected region, multiply connected region. Okay, examples, as I told you, this is one curve and this is hole. This is the domain D. This is the domain D. Only these points. Only these points. Okay. How many holes? This is called doubly connected region. One hole, then it is called doubly connected region. Multiply means doubly or triply, like that. Okay. If I consider, for example, two holes, some region is like this. See, there is one hole here, there is another hole here. Where are the points? Here, not inside the holes, right? These are the points. This is domain D. This is called how many? This is domain D. Okay. No, this is not a. Okay. This is domain D. Okay. This is called how many holes? Two holes are there. This is called triply connected region. This is called triply, not doubly. Two holes means triply. Triply connected region. Triply connected region. And the most important point is note. What is that note? A multiply connected region. A multiply connected region can be reduced to simply connected region. Simply connected region can be reduced to simply connected region by taking cuts. By taking cuts. Okay. Example. For example, see, let me consider one doubly connected region. Okay, a simple logic. This is curve C, and there is a hole here. And where is the D? D. These are the points. These are the points of the domain. So it is a doubly connected region. Doubly connected region. I have to transform this. How this doubly connected region transform to simply connected. See, simply connected domain means which does not contain hole. Remember this point. Now I'm taking what? There is a cut. I'm cutting with a scissor. Here I'm cutting. This is a cut. Then what is the shape of the figure? All of you. Okay, let me show clearly. If this is doubly connected region, okay, I will draw one more figure to understand this concept. See, and this is this one. This is domain D. Now I am taking cut. This is a cut here. What is the meaning of this cut? If I cut by the scissor, okay, here, somewhere, whatever, take one cut for this. Then what is the shape? See, I'm tracing from here onwards. Okay, this, it is like this, and coming to here, and there is a cut. Okay, then again it moving like this. This one. This shape is like this now. Now, where is the domain D here? This is the domain D. Where are the points? All these are the points. Is there any hole here? Here, there is no hole. Here, there is no hole. So, what is this region? Simply connected. So, this region is what? Simply connected. Any doubts? Once again, this is one doubly connected region I'm taking. Let me take one cut here. If I cut here, the shape becomes like this. The shape becomes like this, which does not contain any hole. So it is a simply connected. Let me take one triply connected. This is one curve C. There is one hole here. There is another hole here. One hole and another hole here. Isn't it right? Okay. Now, how to make it as a this is, I'm taking hole means this is C. I'm taking this one C1 and this is C2. Okay. This is the domain D. So these are the points of the domain, not inside the holes. What is this one? Triply connected. Triply connected. Now, what I'm taking, same figure. Okay. This is curve C. Okay. This is C1. Always anti-clockwise, remember. This is C2. Now let me consider cuts. To make it as a simply connected, I'm taking one cut here with scissor, another cut here. Then what is the shape becomes? See, shape becomes this one is equivalent to transform it to. Now this is the figure. Okay. Not exactly, not exactly this. Let me start. See, let me identify the points. I'm taking cut here now. This is cut. This is cut, right? Okay. This is the cut. Now, let me trace from here onwards. From here onwards. Okay. I'm tracing now. From here onwards, this point onwards, if I trace coming to here, okay. Let me go. Yeah. Starting from here, this down. Oh, where is the curve? This is the curve, shape of the curve. There is a cut here, right? Okay, now it is okay, right? Now check this. Let me start here. I'm starting here. It moving like this, and there is a cut here, and cut goes inside. Next, moving like this and coming to here, and this, since there is a cut, moves like this and moving like this, and there is a cut here, so goes inside. Next this, next this. So anti-clockwise direction. What is this one? See, this is C1. Anti-clockwise direction now. This is C1. This is C2. So what is what is the shape here? Let me take. See, the moving traversing is, this is C1, moving like this, right? And this is the direction, and inside this is the direction, right? Okay, this is the direction. Next, so moving like this, and this is the direction. Next, this is the direction, right? What happened? This way. Yeah, this is the direction. Next, inside this is the direction, moving towards this, and next direction is this. Next, this one. Next, this one. See, direction is important. Direction of the curve C1, C2 is not important. Remember this point. Always anti-clockwise direction is very important. Okay, now what is this one? Is there any hole here in this region? What are the points? These are the points. Is there any hole? There is no hole. Okay, there is no hole. There is no hole. Therefore, it is a simply connected. Therefore, it is a simply connected region. This is a simply connected region. Any doubts? Conversion of multiply connected to simply connected. Any doubts? Is this clear?
Yes, sir.
Okay, right. Done. Let us move towards our Cauchy's theorem. Cauchy integral theorem. Cauchy integral theorem, and someone, it is in some textbooks, it is also given as Cauchy's theorem. Cauchy's theorem, simple. Cauchy's theorem or Cauchy integral theorem, both are same. Okay. Now, what is the statement of Cauchy integral theorem? Statement of Cauchy integral theorem. Let f of z. What is f of z? Uxy plus I into Vxy, complex function. F of z equal to Uxy be the analytic function, be the analytic function, and f dash z be continuous. F dash z be continuous in a simply connected domain. In a simply connected domain. In a simply connected domain D, then integral over C. This circle means circulation, closed curve. Whenever over integration the circle is mentioned, means the curve must be closed. Integral f of z dz equal to 0. Integral f of z dz equal to 0 along every simple, smooth, closed curve C. Closed curve C contained in D. Contained in D. Along any simple closed curve, simple and smooth closed curve C contained in D. Contained in D. Now, the statement is very important. Just by applying this theorem, we can solve the problem. And what are the main important points? Remember, first one, f of z must be analytic function. What is meant by analytic function? The function must be derivable everywhere and in its neighborhood also. And in its neighborhood also. Okay. Then what is this? F of z, f dash z is continuous. F dash z be continuous means what? See, f of z is analytic, means it is derivable. It is derivable means what? F dash z exists. Means f dash z exists means f dash z is continuous. In what? Another main important point, in what? Simply connected domain. Simply connected domain means what? Which does not contain any hole. Which does not contain any hole. If these conditions are satisfied, first condition, f of z is analytic. Second condition, f dash z is continuous. Actually, there is no need f dash z is continuous. Okay. Later on, this Cauchy's theorem is modified. That is named as Cauchy-Gorsuch theorem. Cauchy-Gorsuch theorem. Okay. So, only one important condition is what? F of z must be analytic function in a simply connected domain D. Remember this point. F of z must be analytic function. Analytic function means what? It must be derivable at a point and it's in its a small neighborhood also. And what are the necessary and sufficient conditions? Cauchy-Riemann equation. If f of z is analytic, Cauchy-Riemann equations are satisfied. Okay, and converse is what? If Cauchy-Riemann equation satisfied and all the first order partial derivatives are continuous, then f of z is analytic. Okay, now f of z is analytic function in a simply connected domain D. Then what is this one? Integral over C f of z dz value. What is C? This is a simple closed curve C. This is curve C. This is curve C. Okay, and domain D is bounded by what? Where is this curve C? Along simple closed curve C contained in a domain D. Contained in a domain D. Okay, or you can take two ways. For example, this is one curve. This is one curve. This is domain D. This is domain D. Everywhere. Domain D. Right? Where is this curve C? It contained in domain D. It contained in domain D. And point is what? This f of z is analytic. F of z is analytic in D. Then what is the value? Then integral over C f of z dz equal to 0. For example, see. For example, if I consider integral over C function, for example, sine z dz. Evaluate. Question is what? Evaluate integral over C sine z dz, where C is mod z equal to some 2 or 1. You can take any one. 1, 2, 1 by 2, whatever it is. Doesn't matter. Right? What is the solution here? First, C is what? C is the circle. C is the circle, mod z equal to 2. Okay. C is the circle, mod z equal to 2. Means what? Center at 0, 0 with radius 2 units. This is mod z equal to 2. And what is my domain here? This entire is domain. This entire is domain bounded by the circle mod z equal to 2. This is the domain. Now here, what is f of z? Sine z. F of z equal to sine z. Already we proved this. Sine z is analytic everywhere. Is analytic everywhere in D. At every point, the function is differentiable. That is, you can write here. That is, sine z is no need to write. Analytic means you know. So I am not writing this. Okay, analytic in D. Now, according to Cauchy's theorem, what is this? see, remember one more short term. This function f of z, which is quotient of dz. If f of z is analytic everywhere in the domain which is bounded by closed curve C, then what is the integral value? 0. Therefore, using Cauchy's theorem, therefore, just you have to mention the statement, that's all. Using Cauchy's theorem, since it is analytic everywhere in the domain, integral over C sin z dz, f of z value, this one, what is its value? 0. What is its value? 0. Right? Okay. For next, another example. Evaluate. Integral over C. Integral over C. E to the power of sin z square dz, where C is mod z equal to 1 unit circle. Mod z equal to 1 unit circle. Solution. What is here? F of z e to the power of sin z square. Okay. And what is C? Mod z equal to 1. Mod z equal to 1 means what? This is mod z equal to 1. This is 1. Center 0. So this is my domain. This is my domain capital D entire. This is my domain capital D. Then what happened? In this domain, the function e power sin z square is analytic. Analytic means what? It must be differentiable. First point, it must be differentiable. And it must be differentiable at every neighborhood of the point. Every neighborhood of the point. Okay. What is this? Exponential function is everywhere differentiable. Yeah. E to the power of sin z square. For example, if I calculate f dash z, what happened? F dash z, if I calculate e to the power of sin z square, and sin z square derivative cos z square, and z derivative 2z is exist everywhere. Anywhere indefinite, this one in the domain. What is the domain? Mod z equal to 1 domain. Exist everywhere in mod z equal to 1. Therefore, f of z equal to e to the power of sin z square is analytic everywhere. Is analytic everywhere in D. Therefore, using Cauchy's theorem, we have circulation over C. What is C? Mod z equal to 1. One can write like this also. E to the power of sin z square dz value 0. Sin z square dz value 0. Okay. Any doubts? Any doubts? Now, one more problem to clear if any doubt in Cauchy's theorem. Evaluate integral over C. Tan z I am taking. Tan z dz, where C is mod z equal to 1. Where C is mod z equal to 1. Solution. What is f of z? Tan z. F of z is tan z. What is the meaning of tan z? Sin z by cos z. See, all of you, you know this logic theory. If f of z is differentiable, means it is continuous. Every differentiable function is continuous. If a function is continuous, then only it may be differentiated. Remember this point. If the function is continuous only, if it is continuous only, then it may be differentiable. It may be differentiable. That means derivative may exist or may not exist. Okay. So continuity is the main function. First of all, f of z must be continuous. F of z must be continuous. Continuous means what? It must exist. F of z must be continuous for the differentiability. This is the first condition. Okay. Why I'm telling this? Because in the derivative cosine z is there. Here, f of z is not continuous. f of z is not continuous at cos z equal to 0. That means what? When z equal to what values? Plus or minus pi by 2, plus or minus 3 pi by 2, and so many values are there. Now it is not continuous when cos z. I will write when cos z equal to 0, denominator is equal to 0, right? That is, it is not continuous means not differentiable. Not differentiable means not analytic, right? That is, f of z is not analytic. F of z is not analytic when cos z equal to 0. That means when z equal to plus or minus pi by 2, plus or minus 3 pi by 2, and at infinitely many. Okay, plus or minus odd pi by 2. Okay, here, here C is mod z equal to 1. Here C is mod z equal to 1. All these are points saying one more important point here. I think I forgot to tell. If f of z is not analytic at z equal to a, then a is called singular point. A is called singular point. This is one important. Okay, why it's a is called singular point. So all these points are called what? Singular points. All these are called singular points. Now here, what is C is mod z equal to 1. Now I'm giving the picture. This is 1. Mod z equal to 1 curve, and this is 0. Here, the important point is what? Here, the important point is the singularities. The singularities. What are the singularities? Z equal to plus or minus pi by 2, plus or minus 3 pi by 2, and so on are all lie. See, all of you remember what is plus pi by 2 means what? 3 point, what is the value? 14 something by 2. That means 1.07. It is greater than 1. It is greater than 1. That means where is the singularity? Pi by 2 is here. Same logic. Minus pi by 2 is here. Minus pi by 2 is here. Somewhere 3 pi by 2 is here. Somewhere minus 3 pi by 2 is here. Like that. Right? This is my domain D. This is my domain D. And one more logic to check whether the point is inside or outside. What is mod z equal to 1? Put z equal to pi by 2 or minus pi by 2, plus or minus pi by 2. If I take z equal to plus or minus pi by 2, then what is this? Mod plus or minus pi by 2 is the value. This value is greater than 1. Therefore, z equal to plus or minus pi by 2 lies outside mod z equal to 1. It is greater than radius, so lies outside. So this is the main point. All the singularities, similarly other singularities. Okay, z equal to plus or minus pi by 2, plus or minus 3 by 2 lies outside to the circle mod z equal to 1. To the circle mod z equal to 1. Okay, see, once again I am explaining this problem. F of z equal to tan z. Tan z means sin z by cos z. And when this function is not, where this function is not, now onwards I will tell not analytic means this denominator. Not analytic means this denominator is equal to 0. At where this denominator is equal to 0, at those points the function is not analytic. Therefore, at cos z equal to 0 means z equal to plus or minus pi by 2, plus or minus 3 pi by 2, the function is not analytic. Okay, so those are called singular points. And let us see where these singularities lies, whether inside the domain or outside the domain. So I'm taking a picture of this, and without picture you can use this logic. That means in the curve equation, in the curve equation mod z equal to 1, put the singularities. See this value. What is this value? It is greater than 1. Plus or minus pi by 2 value greater than 1. Greater than means 1 means more than radius 1. More than radius 1 means lies outside. Lies outside the domain mod z equal to 1. Therefore, f of z equal to tan z is analytic in mod z equal to 1. Is it correct? Any doubts? It is not analytic outside this region. It is not analytic outside this region. But inside, any singularity is there. Yes, inside this circle, any singularity is there? No singularity. Even in on the curve also, there is no singularity. On the curve also, there is no singularity. F of z is analytic everywhere. You write everywhere. Because on curve C also, we have to take analytic everywhere of mod z equal to 1. Everywhere of mod z equal to 1. Therefore, using Cauchy's theorem, we have, what is this one? Circulation over, what is this? Mod z equal to 1. Tan z. What is this value now? Since the function is analytic everywhere in mod z equal to 1, its value is 0, even though it possesses singularities, but those singularities lies outside the domain. Hence, the function is analytic everywhere in the domain. Its integral value 0 by using Cauchy's theorem. Its integral value 0 using Cauchy's theorem. Any doubts? Still any doubt? You can see this problem also. Evaluate. Let me take, yeah. E to the power of z by z square plus 9 dz, where c is mod z equal to 2. Where c is mod z equal to 2. Okay. Now, solution. What is f of z is here? E to the power of z by z square plus 9. This function is not analytic. Where this denominator is equal to 0, not analytic when z square plus 9 equal to 0. That means z equal to what? Plus or minus 3i. Z equal to plus or minus 3i. Therefore, z equal to plus or minus 3i are the singularities. Now let us see where these singularities lies. Our circle is what? Mod z equal to 2. Our circle is what? Mod z equal to 2. This is mod z equal to 2. So this is 2 and this is negative 2. Right? And what is this one? This is also 2 and this is negative 2. Now what is the singularity? See, z equal to 3i if I consider. At z equal to 3i, mod z equal to what? Mod 3i. That is nothing but 3. 3 is greater than 2. Nothing but see. This is singularity. Sorry, not this. Singularity is 3i. Imaginary axis I have to put. This is 3. And this is negative 3. Somewhere. This is minus 3. This is y-axis. Done? So, the function is analytic ever. This is my domain only. This is my domain capital D. Right? And at z equal to minus 3i also. Z equal to minus 3i. What is mod? Then mod minus 3i. That is also 3. Greater than 2. Right? Z equal to plus or minus 3i singularities greater than 2. Therefore, z equal to plus or minus 3i lies outside the domain. Outside the domain mod z equal to 2. Therefore, f of z is analytic everywhere. F of z is analytic everywhere of mod z equal to 2. Therefore, by Cauchy's theorem, Therefore, by Cauchy's theorem, we have what is the integral value? Integral of what is that? E power z by z square plus 9 dz is its value is what? 0. Its value is what? 0. Any doubts? Yes, any doubts?
Sir, if f of z is non-analytic, then this theorem is not
Exactly.
applicable.
That is the next topic. Now, till now, it is clear.
Yes, sir.
Anybody? And what is the point now? One note is what? Cauchy theorem. Cauchy's theorem is applicable in what domain? Simply connected. Simply connected domain only. Simply connected domain. Applicable in simply connected domain. If D is not simply connected, D is not simply connected, then we have Cauchy extension theorem. We have Cauchy extension theorem. Cauchy extension theorem. What is that Cauchy extension theorem? See, for example, Cauchy extension theorem. Consider, I'm not stating, just I'm proving one part. Consider a doubly connected domain. Consider a doubly connected domain. What is the domain I'm taking? Doubly connected means what? Only one hole will be there. This is curve C and this is C1. Okay. These are the points. This is the domain. All of you, this is the domain. Okay. Convert. To apply Cauchy's theorem, what I have to convert. To apply Cauchy's theorem, I need only simply connected domain. Now this doubly convert doubly connected region into simply connected region by taking what? Already told you, by taking a cut. By taking a cut. That is, now I'm showing this. This is the curve C, and this is the hole. This is C1, this is C1. Okay, and let me consider one cut. I'm taking cut here. This is the cut. So this is equivalence to. Now I'm showing. See, always traversion is anti-clockwise direction. So let me start from here. Anti-clockwise, it is moving like this, moving and coming to here, moving inside. So this is the curve C, right? And this one done, and this and this. So where is the direction now? This one, this one, this one, this one, and this anti-clockwise direction. Correct? Done. And what is C1 now? Observe this one. What is actually C1? C1 direction is what? C1 direction is what? C1 direction is actually what? Anti-clockwise direction, right? C1 is in anti-clockwise. Just for our idea, I'm showing like this. Now, what is this domain now? This domain is what? Any hole is there in this domain? There is no hole at all. So it is a simply connected. It is a simply connected. Okay. Therefore, integral over C f of z dz equal to, listen carefully, integral over C f of z dz equal, that means along doubly connected. What is this C? Doubly connected. I'm writing first thing, first point. Let me consider points here. I'm taking this point as A, this point as B, done, and this point as let me consider one more point here, some D. Already C is over now. D. This is E. This point is E, and this point F. Okay, and some point G, some another point H, like this, right? Now I have to trace this closed curve C completely. Closed curve C, I have to trace this. Okay. Then what is the answer becomes? You write like this, but what is the curve C? Integral over C f of z dz equal to, first I'm tracing from here. This is F, G, F, moving like this anti-clockwise direction, G, H, A, f of z dz, outer curve, this outer curve, this outer curve. Okay, up to here A is over. Next, plus integral up to from A to B, inside A to B f of z dz, A to B f of z dz, plus integral after A to B, what is the traversion from B D E, B D E, okay, B D E, yeah, f of z dz, plus next one is what? EF. Next one is what? EF. F of z dz. Done. After EF, again what? Starting with F, closing with F. Okay. Then what is this is equal to? This is equal to, first one is what? Say, outer curve is what? I can say, yeah, just one point. This is not integral over C. I will take this is integral over C. I have to write again. What is this? Starting with F, 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 okay, F, G, H, A, B, D. I'm writing all this, tracing this curve. F, G, next H, next, where is it? Yeah, H, A, next A, B, next B, D, E, B, D, E. Next one was what? F. Next one is what? F. Okay. What is this domain now? This domain is what? This is simply connected domain. Simply connected domain. Simply connected domain. Done? And this domain can be written like this, splitting into parts wise. And since this simply connected domain, f of z is analytic everywhere. F of z is analytic everywhere inside this domain. Therefore, what is its value? Using 0, using Cauchy's theorem. Using Cauchy's theorem. Left side value 0. Coming to right side, observe this. Coming to right side, FGHA, what is that? F, G, H, A. What is that curve? C. That curve is C. I'm writing C. F of z dz, one value is over, plus integral over AB, f of z dz. This is straight line. Integral over AB, AB. This is the straight line. Done. And what is this? BDE. See, all of you, see this one. BDE. What is this one? Curve C1. Curve C1 in anti-clockwise direction, but actually clockwise direction. But what is curve C1? Anti-clockwise direction. So I can write this as minus integral C1. Rotation is opposite direction. So minus C1 f of z dz. And lastly, EF. What is EF? This is EF. Exactly, EF is opposite direction to AB. EF is opposite direction to AB. So I can write minus integral AB f of z dz. F of z dz. Okay. So which terms are getting cancelled? These two are getting cancelled. So what I'm getting, this is 0 is equal to integral over C f of z dz minus integral over C1 f of z dz, f of z dz. So that is equal to integral over C f of z dz equal to integral over C1 f of z dz. F of z dz equal to f of z, this one. This is Cauchy's extension theorem, is the Cauchy's extension theorem for doubly connected region. For doubly connected region. Similarly, for triply connected region, similarly, for triply connected region, triply connected region, Cauchy extension theorem. Cauchy extension theorem is original curve is C dz. What is triply connected means? Just I'm drawing figure. This is C. There are two holes. One is C1, another one hole. This is C2. Sorry. This is another hole. This is C2. Two holes are there. So then integral over C1 will be there, f of z dz, plus integral over C2 will be there, f of z dz. This is for triply connected. In general, Cauchy's extension theorem, Cauchy's extension theorem for multiply connected region, for multiply connected region is integral over C f of z dz is equal to integral over C1. Multiply connected region means there are, for example, n holes are there. N holes are there. F of z dz and so on. Lastly, nth hole. F of z dz. This is Cauchy's extension theorem. Cauchy's extension theorem. If number of holes are in infinite, then the integral sum of the infinite number of integrals. Okay, and if I do explanation for this, no need of this. Let me write. Now, Cauchy's integral formula. Cauchy's integral formula. Cauchy's integral formula. First one is what? Cauchy's integral theorem. First one is Cauchy's integral theorem. Now, Cauchy's integral formula. Theorem is different from formula. What is the statement? Cauchy's integral formula statement. If f of z is, better you write like this. This is also over. This is also over, right? Okay. If statement is, if f of z is analytic, if f of z is analytic within and on a closed curve, within and on a closed curve C, within and on a closed curve C, and if A, point A, that is a point A is any point, A is any point within C, A is any point within C, then f of a is equal to 1 by 2 pi I integral over c f of z by z minus a dz. Z minus a dz. See, what is please understand this statement first. First one, what is the points? F of z is analytic within and on a closed curve C. So I'm taking one closed curve C. F of z is analytic everywhere within and on a closed curve C. Within and on a closed curve C. Only f of z, remember, only f of z. And a is any interior point. A is any point within A, within C. I'm taking this. See, all of you observe this. What is the function here? F of z by z minus a. F of z by z minus a is the within integration, not f of z. See, in this fraction, this numerator function, f of z is analytic everywhere. It is clearly given. F of z is analytic everywhere. Everywhere. But this entire function, f of z by z minus a, is analytic everywhere. Is analytic everywhere. Just I'm giving a note here. Here, f of z is analytic everywhere of d. But what is the integrand function? F of z by z minus a is not analytic. Not analytic. At what point? At z equal to a, which lies inside the domain. Which lies inside the domain. That means what? Z equal to a is, therefore z equal to a is singular point lies inside singular point lies inside the domain, or C, inside the domain. Therefore integral over C f of z by z minus a. Now this is the function. It is definitely not equal to 0. See, if f of z by z minus a, if this entire function is analytic everywhere using Cauchy's theorem, this function is entirely analytic everywhere, then using Cauchy's theorem, its value 0. But since this is the point z equal to a is a singularity which lies inside the domain, so it is definitely not equal to 0. It is definitely not equal to 0. And what is its value then? And therefore, using Cauchy's integral formula, using Cauchy's integral formula, not theorem, integral over C, f of z by z minus a, these are equal to what? You see this, take this 2 pi I this side, 2 pi I, this integral value is equal to 2 pi I into f of a. This is equal to 2 pi I into f of a. 2 pi I into f of a. Any doubts? Remember this formula. Only in this fraction, the fraction structure, listen carefully once again. The fraction structure, how it is, f of z by z minus a only. Not z square minus a square, not z minus a whole square, not like that. Cauchy integral formula standard structure is, this is f of z, and in the denominator it must be z minus a only. Then what is the answer? 2 pi I into, in this f of z, put z equal to a, that is f of a. That is the answer. This is Cauchy integral formula. Cauchy integral formula. Any doubts? And you have to remember this structure to apply Cauchy integral formula. Circulation over C, f of z by z minus a only, where z equal to a is the singular point, must lies inside. All our previous problem, this z equal to plus or minus 3i. One problem is there, na? Z equal to plus or minus 3i. Yeah, this problem. Z equal to plus or minus 3i. Where are the singular points? Actually, the A point is 3i. Why it is not moving? A equal to 3i. Yeah, plus or minus 3i. Why it is not moving? It's working. Pen is working. Yeah. Z equal to plus or minus 3i are the singular points. These are the singular points. Z equal to plus or minus 3i are the singular points. But those singular points lies outside the domain. Means what? This entire function is analytic everywhere. That is why it is 0. That is why it is 0. Now, in this problem, Z equal to A is the singularity which lies inside. So it is not equal to 0. And it is not equal to 0, and we have to apply Cauchy integral formula then. So formula gives this one. Now, see, let me Cauchy integral formula for derivatives. This is also very important. Very important. This one. Cauchy integral formula. Cauchy integral formula for derivatives. Now, what is Cauchy integral formula? First try. Cauchy integral formula is integral over C. F of Z is here. Z minus A is here. Dz value is what? 2 pi I into F of A. Take this as 1. Take this as equation 1. Okay. Where F of Z is analytic everywhere except at everywhere in C, and A lies inside C. A lies inside C. This is the assumption. Now, differentiating 1 with respect to, I need derivatives, right? Differentiating 1 with respect to A. With respect to A, I'm taking, right? So what is this becomes? With respect to A means integral over C. F of Z is taken as constant. 1 by Z minus A derivative minus 1 by Z minus A whole square into minus A derivative, that's equal to what? This is 2 pi I into F of A derivative with respect to A, F dash A. So that implies integral over C, F of Z by Z minus A. Now what is this? Not 1, so whole square dz. What is this formula now? F dash A. F dash A. This implies derivative formula. F dash A equal to how much? 1 by 2 pi I integral over C F of Z by, if first derivative, then here whole square. Cauchy's integral formula is what? F of A. F of A equal to, there is no whole square here. Now F dash A means there is whole square here. This is the first formula. Cauchy integral formula for the derivative. Right. Again, differentiate with respect to A. Then what is this? F double dash A I will get. 1 by 2 pi I. Integral over C. F of Z is treated as constant. What is this derivative? Minus 2 by Z minus A whole cube into minus 1 dz. This is equal to 2 outside. 2 by 2 pi I. Take this as factorial. Integral over C. F of Z. This is whole square. This is cube. Sorry. F of Z by Z minus A whole cube dz. This is F double dash A formula. Similarly, F triple derivative formula, you will get 3 factorial by 2 pi I integral over C F of Z by Z minus A whole power 4 dz. In general, you have to remember this formula. Cauchy's theorem formula, Cauchy integral formula, and Cauchy's integral formula in general. F nth derivative of a, f nth derivative of a, triple derivative 3 factorial, double derivative 2 factorial. This is n factorial by 2 pi I integral over c. This is f of z. This becomes what? Whole power n plus 1, n plus 1 dz is the Cauchy integral formula, Cauchy integral formula for derivatives, for derivatives. Any doubts? Just once again, how to apply Cauchy integral formula. Cauchy integral formula, this numerator function f of z is analytic everywhere, and z equal to a is inside point, then this integrand f of z by only z minus a. It is not analytic in domain D because a is interior. Okay, somebody asked na if it is not analytic. Yes, now this is not analytic. Okay, at point z equal to a, then what is the answer of this integration? 2 pi I into f of a and remaining derivatives formula. Now let me handle one problem, just one problem. In the next class I will take other problems. Yeah, evaluate that one. Integral over c e power z by z square plus 1 dz, where c is mod z equal to 3, where c is mod z equal to 3. Solution. What is mod z equal to 3 means? Circle with radius 3 units, 3, negative 3, and this is negative 3. This is mod z equal to 3. Done. What is, and one more point. See, I'm talking, first let me always, when a problem is given, first apply Cauchy's theorem. First apply Cauchy's theorem. And just briefly, what this is the, if I consider this as the function, just see, I'm not writing f of z directly because you can try by watching the problem. What is f of z? Actually e power z by z square plus 1. Okay, e power z by z square plus 1. E power z by z square plus 1 is not analytic. Not analytic. At what point? At z square plus 1 equal to 0. Means what? Z equal to plus or minus I. Where are these points? Plus or minus I? Plus I, imaginary axis, y-axis. So this is plus I and this is minus I. Plus or minus I, which lies inside, mod z equal to 3. So therefore Cauchy, now the function, this function is not analytic everywhere. Therefore e power z by z square plus 1 is not analytic. Already I have written. Why I say I will write. Therefore Cauchy's theorem fails here. I cannot apply Cauchy's theorem because the singularities are inside, plus or minus, or the singularities which lies inside mod z equal to 3. If I not apply Cauchy's theorem, then you go for Cauchy's integral formula. Okay, therefore now you write the function f of z, not f of z, sorry, not f of z. Let, what is Cauchy integral? See, whenever apply Cauchy integral formula, what is the structure? Integral over c, small f of z is the numerator part and denominator part z minus a dz. What is this value? 2 pi I into this, in this z replace a, f of a. So let f of z the numerator function, then e power z by z square plus 1. To apply Cauchy integral formula, what is the denominator term? Must be z minus a. But here what is the denominator? Z square plus 1. So let me get partial fractions for this to get that. So what is this is e power z. What is this? 1 by z. If I write like this, since these are linear, I can write I plus I2i. Z cancel. So 2i. Correct? This is I plus I. Correct. Okay. Therefore, e power z by z square plus 1 value is what? 1 by 2i outside I can take e power z by z minus a. That means z minus I. E power z f of z by z minus a. That is a value minus I here. Therefore, integral over c, let me consider now. Z square plus 1 dz is equal to 1 by 2i. Okay, integral over c. E power z is a f of z, z minus a dz. This is also integral over c. E power z by z minus a. A value is what? Minus I here. Okay, I will write that. In this one here, a equal to I. Here, a equal to minus I. That's it. Applying Cauchy integral formula. Now I can apply. Clearly it is there. Applying Cauchy integral formula. We have integral over c e power z by z square plus 1 dz is equal to 1 by 2i. What is this value? This is f of z. So 2 pi I into f of a. A value is what? I. Minus here also 2 pi I into f of a. A value is what? Minus I here. So 1 by 2i. What is f of z? What is f of z? E power z. So 2 pi I into e power I minus 2 pi I into e power minus I. E power minus I. So 2 pi I by 2i. Okay, I will write like this. 2 pi I by I will write. E power I minus e power minus I by 2 I will write. I gets cancelled. So 2 pi into what is this value? Sine hi. Is it correct? Any corrections? E power I. If the question is right, e power, wait, there is a change in the question. E power tz. Sorry, this is in the question. This is e power tz. E power tz. Here also tz. E power tz. T is there. E power tz. So everywhere replace t by tz. Now what is this? In place of z I have to put I. E power it and minus it. Now this is correct, right? Now you can write it minus it by 2a also you can write here. No need of this. Okay, then what is this one? If I simplify this, 2 pi I, this is what? E power it means what? Cos t plus I sin t minus cos t. This is minus plus I sin t whole by 2i. Therefore this is 2i sin theta. 2i gets cancelled. Answer is 2 pi I into sin t is the answer. 2 pi I into sin t is the answer. Okay. Any doubts? I will stop here. Once again, you practice all these problems and theory. Write down the notes.